If you've already read Section 8.5, you know that a number of additional tests for convergence and divergence of a series are explained. And I want to go through and talk about the ratio test to begin with and look at an example. Basically, you kind of think about using the ratio test if the integral test doesn't work. So the things that we're learning in 8.5 are going to be options for when the divergence test and integral test from Section 8.4 don't work. So with the ratio test, we start by finding the ratio R, and R is the ratio of A sub k plus 1 over A sub k. Sorry, that's not quite right. R is the limit of that ratio as k approaches infinity. And basically what we're looking for is this. If R is between 0 and 1, the series converges. If R is greater than 1, the series diverges. Greater than 1 includes infinity. Okay, very obviously greater than 1. And if R is equal to 1, then the test doesn't help. And you have to try something else. So if we get a ratio or a value of R that's equal to 1, we've got to try something else. So with this example, the series of 2 to the k power over k to the 99th power, we're going to think about 2 to the k plus 1 power over the quantity k plus 1 raised to the 99th power divided by 2 to the k over k to the 99th. And we're going to take a limit as k approaches infinity. Invert and multiply. And typically when you get to this step, you can start looking at things that are going to reduce. For instance, where you've got 2 to the k plus 1 power divided by 2 to the k, you can reduce that, and that will leave you just 2 in the numerator. And then the k to the 99th power and the k plus 1 to the 99th power we can't do a whole lot with. Alright, so pulling out the factor 2, because that's a constant. And then we've got k to the 99th power divided by k plus 1 to the 99th power. I'm going to write that as k over k plus 1 all raised to the 99th power. And then think about dividing the numerator and denominator of this fraction by k. That would leave you 1 over 1 plus 1 over k, and then that's raised to the 99th power. So we're looking at 2. If I take the limit as k approaches infinity, this fraction is going to go to 0, which leaves me 1 over 1, and then that's raised to the 99th power. So we get a value of 2 for r. 2 is most definitely greater than 1. So this series diverges. The next test for convergence for a series we want to talk about is the root test. Kind of when nothing else works or nothing else gives you conclusive results, then you try to use the root test. One item that I think is not made very obvious in your textbook is that in order for us to successfully work with the root test, we need to know that the limit as k approaches infinity of the kth, sounds like I have a lisp, the kth root of k, that limit is always going to 1. Alright, in this test, we define p as the limit as k approaches infinity of the k root of a sub k. So if we're going to use the root test on this example, then I'd work on the limit as k approaches infinity of the, not 4, the kth root of the quantity k plus 1 over 2k raised to the k power. Now when you've got a power like this, it makes a whole heck of a lot of sense to take that root, because it simplifies what you've got to deal with when you work the limit. Now we're just looking at a limit as k plus 1 as k approaches infinity of k plus 1 over 2k. Using the rules for working with limits, dividing everything, all the terms by k in this example, I'd have 1 plus 1 over k over 2, and that's going to work itself out and be 1/2. Okay. Now, what are we looking for? If this root p is between 0 and 1, our series converges, which is what we have here. So this series converges to 1/2 by the root test. The other options, of course, p could be a number greater than 1. If that's the case, the series diverges. P is equal to 1 doesn't help you. The test is inconclusive.